Imagine, if you can, a world entirely white. Imagine standing, though no one was there to stand, on the equator of a planet whose every ocean had stopped moving, whose every river had frozen at the source, whose every coast had vanished beneath a shell of ice that stretched unbroken from one pole to the other. There is no wind worth the name. What little of it is not condensed into the frost is cold and dry and very still. Lower and dimmer than the sun you have always known, hangs in a sky drained of most of its blue. There are no clouds. There are no birds. There are no leaves to rustle, because there are no leaves. There are no animals to call, because as far as we can tell, there are no animals. Not yet. Not in any form that would survive the surface, not in any form that would care to look up. There is only the ice. The ice is everywhere. The ice is the ocean's lid. The ice is the continent's coat. The ice is what the rain has become, what the rivers have become, what most of the water on the surface of the planet has become. In some places, it is hundreds of meters thick. In other places, where the geometry of the ancient continents and the cold currents below have done their slow work, it may be more than a kilometer. You could walk in this imagined visit from a place that would one day be called Africa, across an ice plain, all the way to a place that would one day be called Australia, without once seeing open water. You could walk from what would one day be the equator to what would one day be the South Pole, and the temperature would barely change. The whole planet, on its outer skin, has reached a kind of quiet that no surface of Earth has held since. And the strange thing, the thing this hour is going to ask you to sit with, slowly, without urgency, while the ice does not move and the world does not turn back yet, is that this happened. Not in a dream, not in a hypothetical. In the deep past of the actual planet you live on now, in the slow rolling history of the Earth itself, there was a time, perhaps more than once, when this is what the surface of our world looked like. Geologists have a name for it. They call it Snowball Earth. And over the next hour, as the sun moves slowly across whatever sky is above wherever you are now, we are going to walk gently across that ice. We are going to listen to what the rocks have to tell us about it. We are going to ask how the world arrived in this state. We are going to ask how, eventually, it left. We are going to spend a little time inside the long, white, almost silent middle, where the planet held its breath for 10 or 20 or 50 million years before, finally, breathing out. There is no rush. The story is older than rush. Settle if you can settle. Breathe if you would like to breathe. The ice has been waiting for a long time. It will still be here in a moment. Before we step onto the ice, let us be careful about when we are. The Snowball Earth episodes belong to a specific stretch of geological time called the Cryogenian period. The name is taken from the Greek words for cold and birth, cryos and genesis. In the gentle way that names sometimes do, exactly accurate. The cold itself in this period gave birth to much of what came after. The Cryogenian extends from about 720 million years ago to about 635 million years ago. It is one of the three subdivisions of the Neo-Proterozoic era, which is itself the last era of the long Proterozoic eon. The Proterozoic, in turn, is the second of four great eons in the history of Earth. The first eon was the Hadean, when the planet was newly formed and almost unrecognizable. The second was the Archean, when the first life began. The third was the Proterozoic, the age of single-celled organisms gradually learning to do new things. The fourth, the one you live in, is the Phanerozoic, the age of visible life, which began only about 540 million years ago. You are listening to this in the Phanerozoic. Snowball Earth happened in the Proterozoic. The numbers, when laid out plainly, can soften the mind. The Earth itself is about 4.5 billion years old. Life of some sort first appeared, as far as we can tell, about 3.5 to 4 billion years ago. The first complex multicellular organisms, unfamiliar forms of the Ediacaran biota, which we will eventually meet, did not arrive until just after the Cryogenian ended. Animals, as you would recognize them, with mouths and guts and limbs and eyes, did not appear until the Cambrian explosion about 540 million years ago. Plants did not climb out onto land until about 470 million years ago. The first dinosaurs walked the Earth roughly 240 million years ago. The first humans, in any form our species would call human, are no older than 300,000 years. If the Earth's full history were compressed into a single calendar year, with January 1st being the formation of the planet and midnight on December 31st being right now, then the Cryogenian, including both Snowball Earth episodes, would fall sometime in early November. The dinosaurs would walk in mid-December. Modern humans would arrive in the last few seconds of New Year's Eve. We're coming back in this hour to early November. We're coming back to a time before any creature on Earth had bones, before any creature had teeth, before any creature could be said, in any sense most of us would recognize, to be looking out at the world and noticing things. The world we are visiting is not yet inhabited by witnesses. The story of Snowball Earth is, in the deepest sense, a story without observers, until we, several hundred million years later, came along with our hammers and our microscopes and our quiet curiosity, and read it back out of the stones. The stones, fortunately, are patient. They held the record all this time, while waiting for someone to come and ask. Before the ice arrived, there was the matter of the sun. The sun you see today, in whatever part of the sky it has reached as you listen, is not the sun that warmed the Earth in the Cryogenian. It is the same star, in the sense that it is made of the same gases and lives in the same place and has the same name. But the sun changes very slowly over the long course of its life. The sun grows brighter very slowly over billions of years. Around the time of the Snowball Earth events, the sun's output was approximately 6% lower than it is today. That is not a small number. 6% less sunlight applied across the entire surface of the planet, applied across millions of years, is more than enough to tip a climate into a colder state than the climate of any human era. 6% less sunlight alone would make the modern Earth substantially cooler than it is now. 6% less sunlight in the early days of the Earth would, by the simple arithmetic of solar output and planetary albedo, have produced a world frozen solid from pole to pole. Most of the time, in those early days, the world was not frozen solid from pole to pole. This is the gentle puzzle that climate scientists call the faint young sun paradox. The sun was dimmer, and yet the Earth was warm enough to keep liquid oceans, and yet life persisted on the planet's surface, and yet the rocks of the early Earth show in most periods the unmistakable signs of a wet, weatherable, warmish world. The reason, as far as we can tell, is the air. The air of the early Earth was different from the air of today. It contained much higher concentrations of carbon dioxide, methane, and other greenhouse gases. Present in small amounts in today's atmosphere, produce a strong warming effect. They let visible sunlight reach the ground, but trap the longer wavelength heat that the ground radiates back up. They form a thin, gentle blanket between the surface and the cold of space. Without that blanket, even with a brighter sun, the Earth would be too cold to keep its oceans liquid. With that blanket, even with a dimmer sun, the Earth could be warm. For most of the Earth's deep past, the blanket was thick. The atmosphere held enough greenhouse gas to keep the planet comfortable, even as the sun was still warming up to its modern brightness. The early oceans did not freeze. Life evolved in tide pools and shallow seas. The slow chemistry of a habitable planet went on. But the blanket is not stable on its own. Carbon dioxide in particular comes and goes from the atmosphere by long, slow processes. Outgassing from volcanoes adds it, weathering of silicate rocks removes it, the oceans take some up and release some back. Over millions of years, these processes balance each other in a soft, self-regulating way. Over tens or hundreds of millions of years, however, the balance can drift. Continents can rearrange themselves in ways that change the rate of weathering. Volcanic activity can speed up or slow down. Life itself can pull more or less carbon out of the system. In the long lead up to the Cryogenian, something began to drift in the direction of cold. The blanket began, very slowly, to thin. Still 6% dimmer than today, was no longer being held in by quite enough greenhouse warmth. And the planet, very slowly, very patiently, began to drift toward the freeze. The drift had a continent's name. If you could lift yourself up above the Earth of 900 million years ago and look down in the position where the modern continents now sit in their familiar arrangement, a single, vast, irregular landmass. Most of the planet's continental crust at that moment was gathered together. Geologists call this great Proterozoic supercontinent Rodinia. Rodinia is older than Pangaea, the supercontinent most people have heard of. Pangaea would not gather for another 600 million years. Rodinia was Pangaea's distant grandparent, a different shape, in a different ocean, on a colder planet, but similar in the basic fact that almost all the dry land was, for a long stretch of geological time, in one place. Rodinia held together for hundreds of millions of years. Beginning around 820 million years ago, it began to break apart. The forces that drove the breakup are the same forces that are still slowly rearranging the modern continents. Convection currents in the deep mantle, hot upwellings rising toward the crust, cold downwellings sinking back, the whole engine of Earth's interior moving its surface around in a kind of slow geometric dance. The breakup of Rodinia did several things to the planet's climate. It opened new oceans between the fragmenting pieces of continent. Those new oceans, narrow at first and broadening over millions of years, exposed enormous stretches of newly torn coastline to the rains. Coastlines weather. Falling on freshly exposed silicate rock, dissolve a fraction of that rock through slow chemical reactions. Those reactions consume carbon dioxide from the atmosphere. The dissolved minerals run off the land into the sea, where they eventually settle as carbonate sediment, locking the carbon away in the sea floor. This is the silicate weathering thermostat. It is one of the slow rhythms by which the Earth keeps itself temperate. When the climate warms, more rain falls, more silicate weathers, more CO2 is removed, and the climate cools. When the climate cools, less rain falls, less silicate weathers, more CO2 builds up, and the climate warms. The thermostat is mostly self-correcting. It has kept the Earth more or less habitable for billions of years, but like any thermostat, it can be pushed too far. When Rodinia broke apart, it pushed the thermostat hard. A vast new length of fresh weatherable coastline was suddenly exposed to the rain. By the geometry of where Rodinia happened to sit on the rotating Earth was concentrated near the equator, where the sun is most direct and the rains are most reliable. The rain fell on the new rocks. The rocks weathered. The carbon dioxide came out of the atmosphere. The blanket thinned faster than it could be replenished. And as the blanket thinned, the climate cooled. Cooler air holds less moisture. Less moisture means less rain over much of the world. Less rain means less weathering in those drier places. But on the wet equatorial coastlines of fragmenting Rodinia, the rain kept falling, and the weathering kept going, and the carbon kept being drawn out of the air, and the cooling kept deepening. It was, in the long view, a feedback loop. It was a feedback loop the Earth had not been in before, at least not at this scale, since the much earlier Huronian glaciation more than 2 billion years before. And as the loop tightened, the high-latitude oceans began to freeze, and the ice began to do something ice does very well. The ice began to make more ice. The first frosts must have come gently. We will never know the year, of course. We will never even know the millennium, the transition from a warm Proterozoic world to the deepening cold of the early Cryogenian unfolded across millions of years, in a slow tightening that no living creature on Earth at the time would have noticed within a single lifetime. There were no living creatures on Earth, then, that lived in lifetimes recognizable to us. The largest organisms were single cells. The oceans held floating mats of microbes. The land held nothing. No plants, no soils worth the name, no fungi, no anything. The first frost did not arrive in the experience of any witness. It arrived in the geology, slowly, layer by layer, where we can still read it. What probably happened in the rough outlines that the rocks allow us to draw is something like this. The ice that already existed at the highest latitudes began very slowly to thicken. Sea ice on the Cryogenian polar oceans, which had previously waxed and waned with the seasons in something like the modern fashion, began to persist year after year, stacking up into layers that did not melt in summer the way they had before. The ice sheets that existed on whatever Cryogenian continents lay near the poles began, slowly, to grow. The growing ice did something simple and decisive. It changed the color of the planet. Open water, even cold open water, is dark. Dark water absorbs sunlight. The energy of the absorbed sunlight becomes warmth, warming the water, warming the air above the water, slowing further freezing. Open water resists ice. Ice, by contrast, is white. White ice reflects sunlight. The reflected sunlight does not become warmth on Earth. It leaves the planet, going back out into space without ever giving up its energy. White ice cools whatever sits beside it. This is the ice albedo feedback. As ice grows, it makes more ice. As more ice grows, the planet gets cooler. As the planet gets cooler, even more ice grows. Each kilometer of new ice cover increases the planet's reflectivity. Each increase in reflectivity drops the average temperature a little further. Each drop in temperature lets the ice creep a little further south or a little further north into latitudes where it would not previously have lasted. If the feedback is gentle and the air still holds enough greenhouse warmth, the system stabilizes. The ice spreads to a new equilibrium and stops. This is what has happened in the more recent ice ages of our planet's modern history. The great Pleistocene glaciations, in which ice sheets covered Canada and Scandinavia, but never crept all the way down to the equator. Those ice ages were severe, but they were stable. The thermostat held. In the Cryogenian, the thermostat did not hold. The breakup of Rodinia had pulled too much carbon dioxide out of the atmosphere. The blanket had grown too thin. The albedo feedback, once it began in earnest, had nothing to push back against. The ice spread further than it had ever spread before, and as it spread further, it cooled the planet further, and it cooled the planet further, and it cooled the planet further. The southern margin of the polar ice met the northern margin of the polar ice somewhere in the middle latitudes. The middle latitudes, in turn, fell to the cold. The ice swept on, the subtropics, the tropics, the lush, wet equatorial zone of the Breaking Rodinia. Somewhere in there, on a date no one will ever know, the ice arrived at the equator. And when the ice arrived at the equator, the world, in the deepest sense, fell silent. For most of the late 20th century, the suggestion that ice had once reached the equator was considered by most working geologists simply impossible. The reasoning was reasonable. A planet whose oceans had frozen all the way to the equator would, by every climate model anyone could build, become locked in that state. The albedo feedback that had brought the ice down would, having brought it all the way, never let it go. White ice reflecting sunlight would keep the planet permanently cold. There would be no path back to a warm, blue world. The Earth, once frozen, should have stayed frozen forever. Yet here we are, on an Earth that is mostly liquid, with continents not buried under permanent ice, and life flourishing on a planet that has been mostly habitable for billions of years. The model said the freeze was a one-way door. The fact of our existence said the door must have been opened again. This contradiction kept most geologists from taking equatorial ice seriously. And then the rocks began to insist. Beginning in the 1960s, but with growing weight through the 1980s and 90s, geologists working in places spread across the modern continents kept finding the same strange thing. They found glacial deposits, the unmistakable rubble left by ice sheets, in rocks that, when their original positions were reconstructed using paleomagnetic data, had been at or near the equator at the time the rubble was laid down. The rubble itself was distinctive. Tillites, which is the lithified version of glacial till, are sediments full of mixed-up fragments of every size, from boulders to fine clay, all carried and dropped together by ice rather than sorted by water. Dropstones, large rocks isolated in fine-grained sediment, are signs of icebergs floating over deep water and shedding their cargo as they melted. Striated pavements, where ancient bedrock surfaces show parallel scratches from the passage of stone-bearing ice, are the glacier's own signature in the underlying rock. These features appeared in Cryogenian-aged rocks on continents that had been at the equator. They appeared in Australia. They appeared in Namibia. They appeared in northwestern North America, in the Mongolian basins, in southern China, in places that, when their continents were reassembled in their cryogenian positions, had been within a few degrees of the equator. The geology was telling a story the climate model said could not be told. In 1992, a paleomagnetic geophysicist named Joseph Kirschvink coined a phrase to describe the puzzle. He called it Snowball Earth. In a short paper that did not at first attract enormous attention, that the Earth had passed through episodes during which the entire ocean was ice-covered, including at the equator, and that life had survived these episodes in pockets, perhaps near volcanic hotspots, perhaps in slightly thinned ice over warm seafloor, until something released the planet from the deep freeze. In 1998, Paul Hoffman and Daniel Schrag, working out of Harvard, took the idea further in a longer paper in the journal Science. They laid out a comprehensive Snowball Earth hypothesis, arguing that the geological evidence, particularly the strange, thick layers of carbonate rock that sit immediately above many cryogenian glacial deposits, could best be explained by a model in which the planet had frozen completely. And then, after millions of years of being locked under ice, had been released by a very slow buildup of volcanic carbon dioxide. The hypothesis was at first met with intense skepticism. Some of that skepticism remains today in modified form. The full, hard snowball model, completely frozen oceans, no significant areas of open water, is not universally accepted. Some specialists prefer a slushball Earth model, in which a narrow band of open water persisted near the equator, while ice covered most of the rest of the planet. Some prefer hybrid models with intermediate states, but the broad outlines of the picture are now widely accepted. At least twice during the Cryogenian period, ice sheets reached the equator. Whether or not every drop of seawater was frozen, the global state was something close to a snowball, far more frozen than any climate state Earth has been in since. The ice arrived at the equator. The geology says so. The continents reassembled in their ancient positions will not let us off the hook. The world, for a while, was white. What did the frozen ocean look like on the surface that no creature was watching? The honest answer is that we are reconstructing carefully from limited evidence. No film footage exists. No diaries were kept. The atmosphere itself has been mostly recycled many times since, leaving us only proxy measurements in the trapped chemistry of preserved rocks. What we can build from those proxies is a picture full of plausible details and few certainties. But the picture is one we can sit with for a while. The sea ice in the high latitudes was probably thick, perhaps several hundred meters thick in places, slowly thickening over millennia of accumulation as snow fell on the surface and froze, and as the ice itself grew downward into colder water at its base. The thickness was not uniform. Where currents continued to circulate beneath the ice, where geothermal heat from the seafloor warmed parts of the water column, where pressure ridges formed at the boundaries between drifting ice plates, the geometry of the ice would have been complex. In the equatorial regions, the ice was probably thinner. Some models suggest it was as little as a few meters thick in places, where solar heating, even from the dimmer Cryogenian sun, was at its strongest. In these thinner zones, particularly during the long summer months when the sun did not set, the upper few meters of ice would have been clear enough that some sunlight could pass through into the water below. Beneath the clear ice, in pockets of relatively warm water under the equatorial sun, photosynthetic organisms, the floating mats of cyanobacteria that had been the dominant life of the Proterozoic, could have continued, slowly, to grow. This is the slush ball element. Even in the strictest hard snowball models, the ice over the equatorial ocean was probably not a uniform thick lid. It was a textured, varying surface with thinner, translucent zones, refrozen leads where the ice had cracked and resealed, and ridges where moving ice plates had pushed against each other. On the continents, the picture was harder still. The continents that remained near the equator were probably covered by ice sheets thick enough to flow under their own weight, much like the modern ice sheets of Antarctica and Greenland. These flowing ice sheets ground their underlying rocks into rubble and dropped that rubble at their margins. They scoured the bedrock with stones embedded in their bases. They produced, over the long course of the glaciation, the very tillites and striated pavements that geologists would later read. The sky over all of this would have been mostly clear and intensely cold. The atmosphere, very dry, held little water vapor. Most of the water that would normally cycle as clouds and rain had condensed and frozen at the surface. Without clouds, without water vapor, without much in the way of weather, the planetary surface lost heat to space rapidly at night. Daytime temperatures in the warmest equatorial reaches may have crept barely above the freezing point. Nighttime temperatures may have fallen below -50 degrees Celsius. At the poles, temperatures may have been far worse, -80, -100 in the long polar night. The wind, what wind there was, blew almost without obstruction across the white surface. There were no forests to slow it. There were no mountain ranges to deflect it in the ways modern mountain ranges deflect it, though Cryogenian mountain ranges did exist. The wind moved snow, it moved dust, in places where dust still existed. It carved patterns on the ice that no eye ever saw. By any measure that humans now use to define a habitable place, deeply uninhabitable. This is the second slow surprise of the Snowball Earth story. Life persisted. Life persisted in pockets throughout the entire frozen interval. Life persisted in places that the eye, even today, would not recognize as a refuge. We will spend a little time now in those pockets. Beneath the ice, in the dark, warm spots where the planet's interior heat met the cold, pressed-down weight of the frozen ocean, life held on. The most important refugees were almost certainly the hydrothermal vents. Hydrothermal vents are openings in the ocean floor where superheated water, charged with dissolved minerals from the rock below, escapes into the cold seawater above. They are common, even today, along the boundaries between tectonic plates and at volcanic hotspots. In the modern oceans, they support remarkable communities of organisms: tube worms, vent shrimp, archaeal and bacterial microbes that depend not on sunlight but on the chemical energy in the vent fluids. These communities are entirely independent of the surface world. The energy that drives them comes from the chemical reactions between vent minerals and seawater mediated by chemosynthetic microbes that, instead of photosynthesizing with light, oxidize hydrogen, sulfide, or methane or hydrogen gas to produce the chemical energy of life. Sunlight is not required. The food chain begins in the dark. During the Snowball Earth episodes, when the surface was sealed by ice and the photosynthetic life of the open ocean had been pushed to the thinnest, most marginal niches, the hydrothermal vents almost certainly continued to function. The Earth's interior heat does not stop because the surface freezes. Plate tectonics, magmatic activity, mid-ocean ridge volcanism, all of it kept going, as it always has throughout the frozen interval. The vent communities, sealed under their kilometers of overlying ice and water, survived. In addition to the vents, life would have found refuge in other unusual places. Beneath the equatorial ice, where occasional sunlight penetrated thinner sections, photosynthesis could continue at low levels in the upper water column. In cryoconite holes, meltwater pools that form on the upper surface of glacial ice when wind-blown dust absorbs sunlight and melts the ice beneath, microbial communities could persist on the surface itself, isolated in tiny watery worlds a few meters across. Some life may have persisted in subglacial lakes, like the modern Lake Vostok beneath the Antarctic ice sheet, where liquid water has been isolated from the surface for millions of years and yet still hosts microbial communities. Some life may have persisted in the pore water of the deep sediments, where heat from the planet's interior keeps water from freezing even when the ocean above is locked in ice. The list of possible refuges is long, and we will probably never know exactly which were used by which organisms. But the broader pattern is clear. Life on a snowball Earth was not extinguished. Life was reduced. Life was concentrated into pockets. Life waited. This is, in itself, one of the most important lessons of the Cryogenian. Even when the surface of the planet became as inhospitable as it has ever been, even when the great open biosphere of the Proterozoic was reduced to a network of small refugees scattered across the globe, the chain of inheritance never broke. Every organism alive today, including you, descends from microbes that lived through the snowballs. Whatever else was lost, the line continued. The ice covered everything that mattered to most observers. It did not cover everything that mattered to life. How frozen, exactly, was the world? This is the question that has split geologists into two friendly camps for the last 2.5 decades. On one side stands the strong Snowball Earth hypothesis. In its purest form, this view holds that the entire ocean surface was covered in continuous ice, including at the equator. Open water, where it existed at all, was confined to the bottom of polynyas and to a small, possibly occasional thin film of melting at the warmest equatorial ice. In this strict picture, the ocean surface was, for all practical purposes, ice from pole to pole. On the other side stands the slush ball, or soft snowball hypothesis. Based partly on the difficulty of escaping a fully frozen state and partly on certain geochemical evidence, holds that a band of open water persisted near the equator throughout the glaciations. This open band, perhaps tens of degrees wide, would have allowed continuous photosynthesis, continuous evaporation and rain, and continuous biological cycling, even as the rest of the planet was locked under ice. Both hypotheses agree on the basic facts. Glacial deposits really do appear at the paleoequator. Cap carbonate layers really do sit on top of the glacial deposits. Major changes really did happen to the carbon cycle and to the oceans during and after the Cryogenian glaciations. The disagreement is about how complete the freezing was, not about whether it happened. Much of the evidence cuts in both directions. The depth of the cap carbonates, the rapidity of their deposition, and the extreme isotopic excursions they preserve are all easier to explain in a strong snowball model, where the planet's carbon cycle was deeply disrupted for millions of years and then restored in a sudden greenhouse aftermath. The persistence of multiple lineages of complex life, including the eukaryotic algae that diversified during and just after the Cryogenian, is easier to explain in a slush ball model, where photosynthetic refugia near the equator were larger and more continuous than they would have been in a hard snowball. The most likely truth, in the way that complicated truths often are, is somewhere in between. The Earth probably did not freeze completely solid in the strict hard snowball sense. There were probably narrow zones of open water, particularly in the equatorial summer, where some surface biology continued. But the freezing was probably much closer to a snowball than to anything we have any modern reference for. The ice extended to within a few degrees of the equator. The ocean surface was, for the most part, ice. The continents were under ice sheets. The world was, in any honest sense, frozen. We do not need to choose today between the two camps. The honest version of the story is that the planet was very, very, very cold and very, very, very white, and that the exact distribution of remaining open water, while important to the science, does not change the overall fact. The fact is the cold itself. The fact is the duration. The duration is what stops the mind when you let it. The Sturtian glaciation, which is the older and longer of the two main Cryogenian Snowball Earth events, lasted approximately 57 million years. The Marinoan glaciation, which followed roughly 15 million years after the Sturtian ended, lasted approximately 15 million years. The Earth experienced more than 70 million cumulative years of deep planetary glaciation during the Cryogenian. 70 million years. For comparison, the entire age of the dinosaurs, from the appearance of the first dinosaurs in the Triassic to their extinction at the end of the Cretaceous, was approximately 170 million years. The Snowball Earth episodes together lasted nearly half as long as the entire age of dinosaurs. For another comparison, the entire span of recorded human history, from the earliest cuneiform tablets in Sumer to whatever date you are listening on now, is approximately 5,000 years. The Sturtian Snowball Earth lasted more than 10,000 times as long as recorded human history. Modern humans, as a species, have existed for roughly 300,000 years. The Sturtian was nearly 200 times as long as our species has lived. In the long perspective, this is a hard thing to feel. Our minds did not evolve to think on these timescales. We can name them, we can write them out as numbers, but we cannot really inhabit them. The closest we can come is to remember slowly that a stretch of geological time longer than our entire genus has existed was a stretch of time during which the planet's surface was almost entirely ice. Sun was dimmer than today. Life was reduced to pockets in the deep ocean and beneath the equatorial ice, and the ordinary cycles of weather and water and erosion that have shaped our familiar world were, for the most part, paused. The Earth held its breath. It held its breath for a long time. If you had been alive, though there was no you to be alive, at any moment during the Sturtian glaciation, you would have seen on every horizon the same white. You would have heard, in the rare moments when the wind dropped, an almost complete silence. The ice did not move quickly. The sky did not change rapidly. The seasons, if they could be called seasons, modulated almost imperceptibly across the years. Day after day, century after century, 10,000 year after 10,000 year, the surface of the Earth wore the same coat, then 100,000 years more, then 1,000,000, then 10 million, then 20. The repetition is almost monastic, almost peaceful, in a way that has nothing to do with comfort and everything to do with the patient endurance of stone. The Earth, frozen, was waiting. It would be waiting eventually for fire from below. But it would wait a long time first. The planet began to do something the climate models had once said it could not do. The planet began to warm. The mechanism, when scientists eventually worked it out, turned out to be the same gentle, patient process that had cooled the world in the first place, running, this time, in reverse. While the Earth was frozen, the silicate weathering thermostat had stopped working. Without rain falling on bare rock, the chemical reactions that ordinarily pull carbon dioxide out of the atmosphere had ceased almost entirely. The continents were buried under ice, the oceans were sealed beneath ice. There was almost nowhere for atmospheric CO2 to go. But carbon dioxide, in the meantime, was still being produced. The Earth's interior had not stopped breathing. Volcanic activity continued throughout the Snowball State, at mid-ocean ridges, in island arcs above subduction zones, at hot spots like the modern Hawaii or Yellowstone. Every volcano on Earth that erupted during the Cryogenian glaciations sent its share of carbon dioxide into the atmosphere. Every fissure that vented gas added more. The CO2 had nowhere to go. The ocean surface was sealed and could not absorb it. The continents were sealed and could not weather. So the gas slowly began to accumulate. Over millions of years, the atmospheric CO2 concentration climbed. From a starting point that may have been similar to today's level, it rose gradually to perhaps 10 or 20 times higher, to perhaps 100 times higher. The exact peak is debated, but most reconstructions place the eventual atmospheric CO2 during the height of the snowball at roughly 1 to 10% of the atmosphere, many hundreds of times the modern concentration. This is an enormous amount of carbon dioxide. The greenhouse blanket, which had been pulled too thin by the breakup of Rodinia and the silicate weathering pulse that followed, was now being thickened, slowly, by the volcanic CO2 trapped under the ice. The blanket grew. The infrared trapping at the top of the atmosphere intensified. The planet's energy balance, in equilibrium with the cold for tens of millions of years, began very slowly to tilt. It tilted slowly. The albedo of the white surface still reflected most of the sunlight. The accumulated CO2 had to fight against that reflectivity. For a long time, the gas built up without producing any visible warming. The ice did not retreat. The blue sky over the equatorial summer was barely warmer than the year before, or the century before, or the millennium before. But somewhere, on a date no one will ever know, the threshold was crossed. Somewhere on the equator, where the sun was strongest and the ice was thinnest, and the new greenhouse warmth could finally do its work, the surface ice began in the warmest weeks of the warmest summer of a particular millennium to melt. A small patch of dark water appeared. The dark water absorbed sunlight where the white ice had reflected it. The dark water warmed. The warm water heated the air above it. The air above it warmed the surrounding ice. The surrounding ice melted. The patch of dark water grew. The albedo feedback that had brought the planet into the snowball was now beginning to take it back out. The ice did not retreat slowly, the way it had advanced slowly. Once the threshold was crossed, the warming ran away. The thaw was almost violent. Within geologically short stretches of time, perhaps a few thousand years, perhaps a few tens of thousands at most, the Snowball Earth came apart. The equatorial ice melted first, in widening rings around whatever initial breach had opened. As more dark water appeared, more sunlight was absorbed. The atmosphere, still loaded with hundreds or thousands of times the modern level of greenhouse gases, now had a warming surface to act on. The temperature of the surface rose fast. It rose much further than the temperature of the modern world. This is one of the most important and most disorienting consequences of the deglaciation. The end of the snowball was not a gentle return to a temperate Earth. It was a swing into a hothouse, a hyper-greenhouse, in which the equatorial regions probably reached temperatures of 40 to 50 degrees Celsius and possibly briefly higher. The same accumulated CO2 that had taken millions of years to build up under the ice was now warming a planet that had no remaining ice albedo to push back. There was, for a few thousand years, simply nothing to slow the warming down. The mid-latitude ice melted next, then the polar ice. Within at most a few tens of thousands of years, an Earth that had been frozen pole to pole for tens of millions of years had become an Earth that was warmer in many places than the modern tropics. The oceans that emerged from the ice were not the calm tropical seas you might imagine. They were stratified, with strange chemistry, with stratospheric levels of dissolved CO2, with surface temperatures that may have approached the upper survival limits of much of the surviving microbial life. The atmosphere was hot, dry in the upper levels and humid in the lower, full of dust raised from the newly exposed continents and ash from the ongoing volcanic activity. The whole planet was, in a strange new sense, awake. Storms must have been enormous. The first rains that fell, after tens of millions of years of frozen continents, fell on the bare rock of recently glaciated landscapes, rock that was unweathered, mineral-rich, hungry for chemistry. The rain dissolved minerals at extraordinary rates. The runoff carried those minerals into the oceans in vast quantities, already chemically strange from millions of years of isolation under ice, received this flood of new ions and responded with rapid, planetary-scale precipitation of carbonate minerals out of the water column. That precipitation, falling slowly to the new seafloors of the post-snowball world, formed thick layers of distinctive limestone. These layers are still preserved today, sitting directly on top of the glacial deposits left by the ice itself. Geologists call them cap carbonates. They are the post-snowball signature in the rock. They are how, in many places, we know the snowball happened at all. The cap carbonates have a story that is gentle and strange. In the field, they look like ordinary limestone, soft beige to gray rock, sometimes finely layered, sometimes massive. If you were not paying attention, you would walk past them without a second thought. They are not the kind of rock that announces itself, but what makes them remarkable is the layer they sit on top of. Directly beneath a cap carbonate in the Cryogenian sequences of Namibia and Australia and central China and northwestern North America lies a layer of glacial deposit, tillite, dropstones, the unmistakable signature of an ice sheet. And then, with almost no transition, with no intervening layer of normal sedimentary rock, the cap carbonate begins. The implication is that the moment the ice retreated, the carbonate began to deposit. There was no quiet century of slow normal sedimentation in between. The ice ended and the carbonate began, and the boundary between them is, in many places, sharp enough that you can put a finger on it. The carbonate itself is unusual. The chemistry is wrong in subtle ways for normal limestone deposition. The isotope ratios of carbon and oxygen in cap carbonates are far outside the range of typical marine carbonates. The deposition rates were extreme, tens to hundreds of meters of carbonate accumulating in what may have been only thousands or tens of thousands of years. The textures, in some sequences, show ripples and crystal fans and other features that suggest deposition under unusually warm, chemically saturated conditions. All of these features fit the model of a hyper-greenhouse aftermath. A planet emerging from the snowball into a CO2-loaded, intensely weathering, chemically supercharged ocean would precipitate cap carbonates rapidly, with strange chemistries, in just the patterns the rocks preserve. The cap carbonates are the smoking gun. They are the geological equivalent of a held breath followed by a long exhalation. They are what the planet did when it began, after 50 or 60 million years of stillness, to move again. When you stand on a cap carbonate today, in the Otavi Mountains of Namibia perhaps, or the Flinders Ranges of Australia, you are standing on the rock that formed in the first weather after the ice ended. You are standing on the recipe of the thaw. And then there was a second freeze. The Sturtian Glaciation, which is the longer of the two main Cryogenian snowballs, ended approximately 660 million years ago. The recovering Earth, hot at first under the load of greenhouse gases, gradually settled. The continents wore down their first generation of post-snowball weathering. The oceans absorbed the excess CO2 over the next 10 million years. Life in its surviving lineages expanded back into newly available marine habitats. For a few million years, perhaps 15, the Earth seems to have been more or less like Earth's before, a temperate Proterozoic world with continents and seas and microbial mats in the slow patience of a planet not yet ready for visible animals. And then, around 650 million years ago, the cold came back. The Marinoan Glaciation, named for the Merino Formation in southern Australia, where its glacial deposits were first studied in detail, was, like the Sturtian before it, a snowball Earth. Ice reached the equator again, the same kind of evidence, equatorial tillites, cap carbonates above them, isotopic excursions in the carbon cycle, appears in rocks of Marinoan age across the modern continents. The Marinoan was shorter than the Sturtian. It lasted approximately 15 million years, ending around 635 million years ago. But within those 15 million years, the planet went through the same patient cycle again. Ice spread, weathering paused, volcanic CO2 accumulated, the albedo threshold eventually broke. The thaw came, a second cap carbonate sequence formed. The Earth had now been, in the geologically recent past, a snowball twice. The hypothesis that the snowball state was a single anomaly was off the table. The Cryogenian was a period in which the Earth, for reasons still being worked out, repeatedly fell into a deep frozen equilibrium, held there for millions of years, and then, by the slow accumulation of volcanic CO2, escaped. The cycle ran at least twice. Some researchers have proposed signatures of additional smaller glaciations in the same period, though these are less universally accepted than the two big ones. What is striking, when you look at the timeline closely, is how soon after the second glaciation, life began to do something it had never quite done before. Within roughly 20 million years of the end of the Marinoan snowball, in the rocks of the Ediacaran period that immediately followed the Cryogenian, the first large, soft-bodied multicellular organisms appear in the fossil record. The Ediacaran biota, strange flat fronds and quilted forms and disc-shaped creatures whose biological affinities are still debated, represent the first widespread visible life on Earth. A few tens of millions of years after that, in the early Cambrian, comes the Cambrian explosion. Almost every major animal phylum that exists today shows up in the fossil record within a stretch of about 20 million years. The Earth, having spent billions of years as a microbial world, suddenly fills with trilobites and brachiopods and primitive mollusks and the first vertebrates. The relationship between the Snowball Earth episodes and the rise of complex life is not simple. The two are not necessarily cause and effect, but the timing is suggestive. After the planet had passed twice through the deepest freeze in its history, after the cycles of intense greenhouse and deep glaciation had churned the surface chemistry of the oceans, after the carbon and oxygen and nutrient cycles had been disrupted and restored on a scale that no later interval of Earth history would ever match, life moved. Life moved into shapes we would recognize, the Ediacarans, then the Cambrians. The first eyes, the first jaws, the long unfolding into the world that would eventually hold us. The Earth does not, as far as we can tell, freeze that completely anymore. The conditions that produced the Cryogenian snowballs were specific. They required a particular configuration of continents, a particular weakness of the greenhouse blanket, and a sun still dim enough to be tipped past the threshold. Since the Cryogenian, the sun has slowly brightened. The continents have rearranged into different configurations. The biosphere itself, especially after the spread of land plants and the long burial of organic carbon, has changed the chemistry of the atmosphere in ways that resist a return to such an extreme cold. The Earth has had ice ages since, many of them. The Pleistocene ice ages in the last few million years have been severe, but none of them has approached the scale of a snowball. None of them has dropped the equator below freezing. None of them has held the planet in its grip for 50 million years. Whether the Earth could ever fall into such a state again is an open question. Most climate scientists believe the present configuration of the planet is fairly safe from a true snowball, even under significant perturbation. The thermostat of silicate weathering, modulated by a now luminous sun and a complex biosphere, is robust. We are unlikely to see ice on the equator again, but the past is not nothing. The fact that the Earth froze twice deeply for tens of millions of years at a time sits in the rocks like a quiet lesson about what this planet has been capable of. The systems we depend on, the greenhouse balance, the silicate thermostat, the ocean circulation, the long flexibility of life, are not infinitely stable. They have in the deep past been pushed past breaking points. They have crossed thresholds. They have, on at least 2 occasions, locked the entire surface of our world into a frozen still that lasted longer than every dinosaur era combined. Whatever comes next, the Earth has done strange things before. It is good sometimes to remember that. So we have walked slowly across the snowball. We have stood in our imagined visit on the white equator where no creature could stand, and we have watched the dimmer Cryogenian sun cross a thinned blue sky. We have followed the slow drift of greenhouse gases out of the atmosphere as the breakup of Rodinia opened too many wet new coastlines. We have watched the ice creep down from the poles and the world's seas freeze over, and the runaway albedo carry the planet into a state we did not think it could enter and could not, once entered, leave. We have visited the deep refuges where life kept on, in hydrothermal vents on a sealed sea floor, in cryoconite holes on the equatorial ice, in subglacial lakes never visited by daylight. We have sat with the long, white, almost monastic stillness of 50 million years of frozen middle. We have felt the slow rebuilding of the greenhouse beneath the ice by volcanoes that did not stop because the surface had stopped, and we have crossed, with the planet, the sudden threshold into the hot, wet awakening of the Cap Carbonate world. We have watched it happen twice, and we have sat with the strange, gentle suggestion, not quite proof, not quite cause, but a coincidence too patterned to ignore, that out of those frozen interludes came, eventually, the first widespread complex life this planet has ever held. As if the cold were a kind of long pause that life needed before it could try the next thing. As if the world had to hold its breath for 50 million years before it could finally exhale into Ediacaran fronds and Cambrian eyes. The story does not need a moral. The rocks do not deal in morals. The story for tonight is simply what happened. A world whose oceans froze, a world that thawed, a world that went again into the freeze and came out again, and then, gradually, settled into the warmer pattern we have inherited. If you have stayed with this voice all the way to the white equator and back, thank you for the company. If you have drifted off somewhere along the Slushy, thank you for that too. The story is patient. The Earth is patient. Whatever drift carried you was probably the right drift. Outside, wherever you are, the air's warmer than it was during the Cryogenian. The sun is brighter than it was. The oceans are mostly liquid. There are clouds when the weather is right, and rain when the weather is right. And somewhere, possibly very near where you are now, there's a small piece of the long blue Earth that is doing exactly what such a piece does. Being mild, being gentle, holding the long inheritance of 3.5 billion years of trial and survival and slow recovery. Sleep well, if you are sleeping. The ice has been gone for a very long time. The Earth for now is warm, and the rocks, as always, are still listening.